Hi guys, I apologize for not being able to be with you for the first couple classes here, but I wanted to make these videos so that you can learn a little bit about the class and also get all the material that we've been that we would be covering these first couple of days, so that we can hit the ground running on the next day. So let's go ahead and start. Let me first start by introducing myself. My name is Andy Rosen, and I'm actually a full-time high school math teacher at Carlsbad High School, and I teach part-time here at Palomar College as well. And yeah, so I'm really looking forward to teaching this class, and certainly looking forward to meeting you guys on Wednesday. One useful resource that I want to share with you right from the very beginning here is my website, rosenmath.com. Let me show you around that website. As I said, I am a full-time high school teacher. So the stuff on the right side where it has my name and the phone number, don't worry about the phone number. That's my classroom phone number. I'm not there over the summer, so that's not really relevant. But certainly the email address can be very useful. In fact, feel free to email me even these first couple of days. I will definitely have access to email. So I'm happy to respond to you if you have any questions even before I get to meet you on Wednesday. On the left side, there's a bunch of information for Carlsbad High School. It doesn't really apply to you guys. Under Palomar College, Math 115, we'll go to that link in just a second. But I do want to point out just really briefly here where it says grades. Right now, let me see if I can make this happen. No? Guess not. So where it says grades there, that will become a link, and then that link, I will be posting grades on this website when we have some, once we have taken some quizzes and tests and so on. Anyway, I'm going to go ahead and click on Math 115 there. And here is our schedule for the entire summer, basically. Let me point out a few things on this website. First of all, that first day there, it has a syllabus. We'll go to that in a minute. The first 2 days, I'm sure you've already found because you're watching the video. The first 2 days, I also have a link to these videos that I've been creating for the site, for this class. And then each of those days, it says what sections we're covering. If there's a quiz and what it covers, if there is a quiz, if there's an exam, what that covers, and so on. And then each of those lessons also is a link. So let me go ahead and click on this first link here. Each of these links is to a PowerPoint handout. So all of my lessons are on PowerPoint, and so I created these links, these handouts, so that you can use them to take notes. So what I would encourage you to do is print these out ahead of time. Use them then to take notes. So you're not spending the whole class copying everything down. You can just fill in the stuff that you need to as we go, and you can pay more attention to the lesson. So I certainly encourage you to do that if that's something you'd like to do. In fact, you might want to just pause the video now because we are going to be doing that lesson on sections 1.1 and 1.3. We'll be doing that lesson as part of this video. So you might want to pause the video, print out that handout so you're ready to go. Now, as I mentioned, I will be doing all the lessons on PowerPoint. I will be writing on, interacting with these PowerPoints, doing the problems, filling in the blanks, and so on. And then at the end of the lesson, I will be saving all that writing. And then this link here where it says sections 1.1 and 1.3, for example, after I'm done teaching the lesson, that link will get replaced with a different file that has all the writing on there. So if for some reason you have to be absent, if you, maybe I went too fast and you missed something, if you took some notes but you're not sure that you wrote down the correct information, all of this will be here so that you can see exactly what we did in class, so that you don't need to borrow anybody's notes, or you don't need to guess. You have all that as a resource. On the right side has all the homework assignments. My intent is only for you to do the odd problems. If you want to do them all, you can do that, but only the odd ones are in the back of the book. Also, I want to point out I did it by section number rather than the page number. Part of my motivation for doing that is if you have an older edition of the textbook, we'll talk about which edition I'm using in just a second. But if you have the previous edition, it will also work fine. Okay, it's still the section numbers are the same, the problem numbers are the same, so you won't have any issues if you have the previous edition of this textbook. Anyway, let's take a look at the syllabus. So there's all the information at the top there, where we're meeting and so on. Office hours, I intend to get to class every day 30 minutes early, so that if you want to come and ask questions before class, you can do that. My phone number is there with an extension. I'm going to tell you right now, I don't have an office. That extension is not attached to any actual phone. And so if you left me a voicemail, honestly, I don't remember the last time I checked my voicemail. So I don't use the phone. Email me. I'll email you very quickly back. So definitely email is the best way to get hold of me. The book we're using is Trigonometry 4th edition by Cynthia Y. Young. As I said, if you have the 3rd edition, that will also serve you just fine. For this class, a scientific calculator is required. If you have a graphing calculator, that is also perfectly fine, but is not necessary. Scientific calculator is fine. If you do not have a scientific calculator, you can buy one at Walmart for like $10. Okay, do not spend more than $20 on a calculator unless you want the graphing calculator. Let me show you briefly what they look like. This is an example of a scientific calculator. Not a ton of buttons, and definitely a small screen here. But it does everything we need to. So, okay, whatever times whatever. Okay, whatever. So that's what it looks like, but it's a small screen. Again, you can buy something like this for $10 at Walmart or Rite Aid or lots of other places. This is a graphing calculator, which is great. These are awesome. And if you're going to be taking some higher level math classes, you may find that you need one. However, if you're just taking this class and nothing else, you don't need to buy a graphing calculator for this purpose. Notice the screen is a lot bigger, a lot more buttons. In fact, it doesn't say at the top, but on the packaging, it'll even say graphing calculator. Really, all you need is a scientific calculator. Honestly, the most important things is make sure that either there's buttons that say sin, cos, and tan. We'll talk about those today, and those will be the core of everything we do in this class. So you definitely need those. Some calculators, instead of this, they just have a button that says trig, so T-R-I-G, and so all 3 of those buttons will be hidden within that one button. So that also is perfectly acceptable. As long as it says scientific calculator, you're good. As long as it has more than just plus, minus, multiply, divide, you're good. Okay, back to our syllabus. All class assignments must be done in pencil. Work done in ink will not be given credit. So make sure you do in pencil. Class website, I already talked about that. Everything's done on PowerPoint, posted on my website. Especially useful if you're absent or you wish to review a lesson. If you don't have PowerPoint, actually, I take it back. They're all saved as PDFs, so even that PowerPoint viewer is irrelevant. Homework. On the class website, a list of homework assignments for the course has been provided. Guys, these assignments are not collected or scored. I'm not going to be looking at your homework, but it's a good idea to do and understand the homework. You really want to do it anyway because, of course, all tests and quiz questions will be based on that homework. Quizzes, we have 7 quizzes throughout the course as listed on the website. Each quiz is 10 points. I do not do makeup quizzes, but you are allowed to drop your lowest test score. In fact, it will automatically be dropped. So if for some reason you have to be absent for a quiz, then I'll give you a 0, and then that one will just end up being dropped. Okay, so so I don't do makeups. Exams, there are 4 exams throughout the course. Each exam is worth 100 points. Once again, there are no makeup exams, but I will drop your lowest exam score as well. So so if you're ever absent for an exam, then it'll just be a 0, and that one will be dropped. Final exam is 200 points, and will be given on, that is not the right date at all. It will be given, our schedule is here. Oh, that is the right date, it's the wrong day of the week. It will be given on Thursday, July 25th. So, it's not a Monday. And of course, you may not drop your final exam score. There's a funny comic that'll make more sense after we start talking about this class. Grading scale, so, just how I score A, B, C, D, F, etc. Miscellaneous participation and attendance are not part of your grade. Okay? I'm not going to be grading your participation, but you want to participate. You definitely want to be there. Students who regularly attend class and participate will find that they understand the course material more fully. Not only that, it just makes it more of an interesting experience for you. So I strongly encourage you to participate. Students are encouraged to work together for this class. That includes working on homework assignments and preparing for exams. The exception, of course, are quizzes and exams. I don't do group quizzes. I don't do group tests. Sorry, it just doesn't work that way. Students with disabilities need to meet with me during the first week of class to discuss testing accommodations. Obviously, that'll have to be Wednesday or Thursday, but definitely talk to me right away. If you feel you are falling behind in the course, please don't hesitate to approach me with questions. I'm available before and after class to help students who need help. Also, there's the Math Learning Center at the San Marcos campus. I don't know if there's a TLC here at the Rancho Bernardo campus, but certainly there are tutoring services available to you. If you use the Math Learning Center, you have to sign up for a 0-unit, no-cost course, and all that information is on their website. Inappropriate behavior such as cheating or excessive disruptiveness may result at the discretion of me in a student being dropped and or a grade of F being recorded. That has never been an issue, but I have it on there just in case, just to be on the safe side. Student learning outcomes. Okay, here are the things. By the end of the course, you will be able to do the following. You will be able to use trigonometric functions to solve application problems involving unknown sides of right triangles. You will be able to solve equations involving trigonometric functions. You will be able to analytically evaluate the 6 trig functions of angles of measure that are multiples of 30 degrees and 45 degrees. And you will be able to use basic identities to verify trigonometric identities and to simplify trigonometric expressions. Okay, so those are all the things that you will be able to do by the end of the course. Cool. All right, let's get to our lesson. And so this first section is all about angles, degrees, and triangles. So we're covering 2 sections today. That's our first one. Everything we're going to be learning in this course, we're going to have to build off of something. So we're going to start by kind of laying the groundwork. I will tell you, especially for this first section, you may find that actually, maybe even for a lot of this first unit, or for this first lesson, the whole thing, you may find that a lot of this is review, and that is completely fine, and that's a good thing. But I want to make sure that we're still going over it to make sure that we're all using the same notation, the same vocabulary, and certainly, even if you've seen it before, maybe it's been a while, so it's definitely worthwhile to review. So first off, and I want to tell you also, a lot of the things we do in this class, especially today, are going to be based on things you've seen specifically in a geometry class. So a lot of the vocabulary and so on will come from that. One last thing I want to mention before we start. Obviously, this is a video on YouTube. I strongly encourage you to pause the video throughout the lesson whenever you need to, if you want to, if you're copying stuff down and so on. There will come points where maybe I ask you to do a problem. I may not put a space on the video because there's not much point. I would encourage you to pause the video so you have time to do it before you resume and hear answers and so on. Okay, here we go. Definitions. A ray starts at a point and extends forever in one direction. Okay. If it went in both directions, that would be a line. But going in only one direction, we call that a ray. When a ray is rotated around its endpoint, so that little red circle there is the endpoint. When a ray is rotated around its endpoint, an angle is created. And so this is the angle that we're looking at here. So there are 2 different ways to do this. So the blue one is that ray we started with. And then we could either rotate it to go up. This direction, by the way, I would point out is counterclockwise. I'll abbreviate that CCW for counterclockwise. If we're going this way, I'm going to abbreviate that CW for clockwise. And I'm not even kidding. I absolutely look at a clock every time I have to remember which way is clockwise and which way is counterclockwise. Whatever. It is what it is. But so there are 2 different ways we could rotate that ray to get the new red ray there. The one we start with, that blue ray, we're going to call that the initial side. That's basically where the angle starts. And then after we've done that rotation, either up or down, we're going to get a new ray. We call that the terminal side. I want to point out that if we rotate counterclockwise, we're going to refer to that as a positive angle. And if we rotate clockwise, we're going to count that as a negative angle. Okay, and so the direction that we rotate definitely affects whether we get a positive or a negative angle. Okay. Also, I want to point out for each of these angles, the initial side that I've drawn here has been a horizontal line moving off to the right. When we're graphing in the Cartesian plane, meaning in the xy plane, the initial side will generally be the positive x-axis. So, for example, if I were to put the Cartesian plane here, here's the y-axis, I missed. Try that again. So here's the x-axis. So notice that this blue initial side here is the x-axis. Okay, that's all I'm talking about. And I don't want to confuse things here too much. Hopefully I haven't already. But yeah, we're going to place it so that that red point, that end point, is the origin, and the initial side is the x-axis. Okay, so we're going to be measuring angles in different ways in this class, but for a good chunk of time here, we're going to be using what are called degrees. So one way to measure the size of an angle is by using degrees, and then one complete rotation has a measure of 360 degrees. Anybody who's done tricks on a skateboard knows, doing a 360 would be going all the way around. Now, one of the things we're going to be using is for our variables, a lot of times a variable use the letter x. When our variable is an angle, we're actually going to be using the Greek letter theta. So it looks sort of like an O with a line through the middle. When I draw it, I'm going to kind of draw an O and then put a little curly Q at the top. This is going to be what my thetas look like. So again, it's a Greek letter. That letter is what we're going to use, not always, but generally we're going to use that for a variable for when we're referring to an angle. Some special names of angles here. A right angle is 90 degrees. A straight angle is 180 degrees, so halfway around the circle. If it's less than 90, we call it acute. And if it's between 90 and 180, we call it obtuse. We don't really have a name for what if it goes between 180 and 360, because generally if it's over here, rather than going this way around, we'll go this way around instead. Or at least to refer to it, to describe it, we would go that way around. So we'd probably still call that obtuse. Anyway, again, you probably heard these words before, maybe even elementary school, I don't know, but I want to make sure we're all using the same words. Some other things maybe you've seen before. Two angles are complementary if their sum is 90 degrees. These two, again, more Greek letters here. This Greek letter is alpha. It looks sort of like a fish. This Greek letter is beta. It looks like the letter B with a little tail at the bottom. And notice that in that picture here, alpha and beta, when you put them together, you get that right angle. So we could say that alpha plus beta is equal to 90 degrees. Okay. So complementary means they add up to 90, and we call them complements of each other. If two angles add up to 180, we call them supplementary, and we say that these angles are supplements. Okay. Please notice that complements, when you put them together, you create a right angle. Supplements, when you put them together, you create a straight angle. So for this problem, let's say we want to find x, we would observe, oh, look, when you put those two angles together, they form that straight angle. They form 180 degrees. So these two angles must be supplementary. So I can write the equation 3x plus 15x equals 180. And then I can use this equation to solve for x. So we get 18x equals 180. Divide by 18, we get x equals 10. Okay, so we found our x. Continuing with our vocabulary, our terminology here. A triangle is a three-sided figure. Yeah, that one I certainly hope you've seen that before. So a triangle, 1, 2, there's three sides. We'll get into classifying some special types of triangles in a minute. Some important observations here to make, though. One of them here is that the sum of the angles of a triangle is always 180. If I take all three angles and add them together, I'm going to get 180. So if two angles of a triangle are 16 and 96, we want to find the third angle. Well, again, if I don't know the missing angle, two of them are 16 and 96. If I add to that the third angle, here, let's practice using theta for an angle. If you put x, I don't care if you put x. It doesn't matter what letter you pick. But I'll put theta just to practice. And I know that adding all three angles together gives me 180. So if I can combine those, we get 112 plus theta equals 118. Nope, 180, sorry. Subtracting, we get theta is equal to 68. So the missing angle is 68 degrees. There we go. There are a few types of triangles we need to talk about. Some will be useful today. Some will be going to be useful for the whole course. So first one's equilateral. An equilateral triangle has three congruent sides and also three congruent angles. Now, the sides can be anything. Maybe they're all 7s or maybe they're all 10s. But I want to point out that the angles, remember, not only are they all equal, they also all add up to 180 because it's a triangle, which tells me that every single equilateral triangle, the corners are going to be 60 degrees. Every equilateral triangle, they're all going to be 60. Okay, and that's going to be really useful for us before we're done today. Another special type of triangle here is called an isosceles triangle. An isosceles triangle has two congruent sides and two congruent angles. Now, the two congruent sides are called the legs, okay? And then the third side, I don't think I have it labeled here. The third side, we call that the base. I don't know if that will come up. But basically, two sides are congruent. We call those legs. By the way, congruent, I should have said this earlier, congruent means the same. They're equal. They have the same length. Now, I want to point out, it's not just any two angles that are congruent. If these are the two sides that are congruent, then these are the two angles that have to be congruent, right? It's basically whichever leg is congruent, across from that, we're going to find the congruent angle. So if those two legs are congruent, then the two sides that I've marked are also congruent. Okay, now, the next type of triangle that we want to talk about is called a right triangle. A right triangle has one angle that measures 90 degrees. Okay, and please notice I've labeled that in the picture with a little box. The side across from the right angle, we call that the hypotenuse. And then the other two sides we call legs. Okay. By the way, really quick side comment. It is possible to have a right angle that is also, it is possible to have a right triangle that is also isosceles. Here's my right triangle. The isosceles part comes from having two legs that are congruent. Now, that won't be true for every right triangle, but it is possible to have a triangle that is both a right triangle and also an isosceles triangle. Erase that. Okay. Now, the right triangle. This is one that is going to be hugely important for this class. We're going to be using right triangles a lot. So it is really important that we remember what it is. Also, when I use the word hypotenuse, we all need to understand right from the very beginning, the word hypotenuse means the one that's across from the right angle. Now, some of you may have learned, oh, hypotenuse, that's the biggest side of the right triangle. And that is true. Hypotenuse will always be the longest side. But if you don't know all the numbers, if you don't know all three side lengths, that won't help you. But it is important to notice hypotenuse is always across from the 90. Okay, now in a right triangle, we have a special theorem here called the Pythagorean Theorem. Again, you've probably seen this before, and if so, that's great. If not, let's talk about it. In a right triangle, a squared plus b squared equals c squared, where c is the length of the hypotenuse, and where a and b are the lengths of the legs. So a squared plus b squared equals c squared, you've probably got that burned in your brain, but it is really important that when you use that, c is always the hypotenuse. C is always the side that is across from the 90 degrees. The a and the b can switch, that doesn't matter, but the c has to be across from the 90. Okay, so let's try this problem here. We have a 10-foot ladder and wanted to reach a height of 8 feet when leaned against a wall. How far from the wall would you put the base of the ladder? Okay. So here's my building. Here's the ground. Here's my ladder. I'm a terrible artist, but I try. Here's my ladder. We're told that we have a ladder that is 10 feet tall, and we want the height of the ladder. We want the top of the ladder to reach a height of 8 feet. And the question is, how far from the wall should we put the base? Basically, how far from that building should the bottom of the ladder be? So there's my x. And of course, hopefully the wall is straight up and down, so I can put a right angle there. So Pythagorean theorem, a squared plus b squared equals c squared. Remember, c has to be across from that 90. So in this problem, c has to be 10. So I'll do x squared plus 8 squared equals 10 squared. Again, the 8 and the x can be switched, but the 10 has to be where it is. So x squared plus 64 equals 100. Subtract the 64 over, so we get x squared equals 36. And then finally square root both sides. The square root of 36 is 6. Some of you may be thinking, wait a second, should there be a plus or minus on that 6? I'm willing to bet there are not very many of you that are thinking that, but some of you might be thinking it. Because x is a length, we only need the positive version, so we don't need the plus or minus. Okay, let's try this problem. Find x. So for this problem, the hypotenuse is 7. So let me put really quickly here. We need c to be 7 for this problem. So when I set this up, I'm going to do x squared plus 3 squared equals 7 squared. So x squared plus 9 equals 49. Subtract the 9 over, x squared equals 40. Okay, and now we're going to square root both sides. So x equals the square root of 40. Now let's talk about that. Some of your quizzes will allow a calculator, and some of them will be non-calculator. Some of the tests, every test will have a calculator part and a non-calculator part. So some problems you will be asked to do without a calculator, and this is probably one of them where I would ask you to do this without a calculator. So you couldn't just type that in your calculator, get a decimal of 6 point something, I don't know. But the square root of 40 is a decimal, so there's not a whole answer. But I do expect you to be simplifying radicals in this class. When I give you a question that is non-calculator and there are radicals, I expect it to be simplified completely. So let's talk about what it means to simplify this radical. There are lots of different ways. If however you learn to simplify this, go for it. That's great. Let me show you a way that I found that works for my students. I'm going to make a number tree for the number 40. So 40 is 2 times 20, which is 2 times 10, which is 2 times 5. Okay. So what that tells me is that 40 can be written as 2 times 2 times 2 times 5. I'm just looking at the numbers at the bottom of each branch. Now, to simplify a radical, here's the thing. Any factors that have a partner are allowed to come out. Okay, in fact, the story I tell is, all 4 of these things, 2, 2, 2, and 5, they're all inside the house. They're only allowed to leave the house if they've got a buddy. Well, the 2s have a buddy, so I'm going to put a 2 on the outside, right? There's a pair of 2s on the inside. They're allowed to leave the house. And so when they leave the house, there's a 2 on the outside. The other 2 and the 5 don't have partners. So the 2 and the 5 have to stay inside the house. And when they do, they're going to multiply. So 2 times 5 gives me 10. So the simplified version of this, the simplified answer here is 2 times the square root of 10. Again, lots of different ways to simplify. This is just the way that I found students find to be approachable. But however you do it, you need to make sure you know how to do this without a calculator. Okay, so it's interesting to observe for these two problems. This problem, I got an answer that was not a whole number. It was a radical. It was a decimal. On this example, I did get whole numbers, right? The two sides that were given were 10 and 8, and the missing side was 6. If you have a right triangle where all 3 sides are whole numbers, we call that a Pythagorean triple. So a set of 3 integers is a Pythagorean triple if they satisfy the equation a squared plus b squared equals c squared. The only reason that this might be useful is it could save you some time and some work. it's possible to use this to solve Pythagorean theorem problems without actually going through the process of squaring stuff and subtracting and so on. So, for example, these are three of the most common Pythagorean triples. These are, if you're going to commit any of them to memory, these are the three you probably want to do. There's 3, 4, 5. Again, that is because if I do 3 squared plus 4 squared, that is equal to 5 squared. 5 squared plus 12 squared is 13 squared, so that's the second one. And then 8, 15, 17 also satisfy. So all three of these are useful. Now, but here's the thing. It doesn't only work with triangles that are 3, 4, 5. Oh, I should mention also, if you've got a triangle, remember, the hypotenuse is always going to be the biggest side. So on these problems, the biggest number is always going to be the hypotenuse. So the 5, the 13, the 17, those are always going to be the hypotenuse for their triangles. But it's not just these numbers. Not only is it these numbers, it's also any multiples of these numbers. So for example, instead of 3, 4, 5, I can double all those numbers and get 8, or 6, 8, 10. Those are the three sides of the triangle we just worked on, that we saw earlier. I could take all three numbers and multiply them by 10. So I get 50, 120, and 130. Okay, these would also be the sides of a right triangle. I can multiply all the numbers by 4. So we get these three. So these would all be good examples. So to show you how this might be useful, let's find x for this problem. Now, let me first just mention, there is absolutely nothing wrong with saying, you know what, I'm just going to do 9 squared plus 12 squared equals x squared. I'm going to solve the equation for x. Awesome, go for it. But if you notice it is a Pythagorean theorem, you can save yourself some work. If you notice that 9 is 3 times 3, and 12 is 3 times 4, we've got a 3 and we've got a 4, so this must be a 5. So 3 times 3, 3 times 4, this will be 3 times 5. So x equals 15. Okay, I notice, hey, look, there's a 3 and the 4. I guess the next one must be a 5. Again, you would get the exact same answer if you set up an equation like we did earlier, but if you notice this, you can make your life a little bit easier. Okay, how about this one? 40, 50, and x. Now, again, it sure looks like that 3, 4, 5 triangle, but again, remember, if you're doing the 3, 4, 5 triangle, the 5 has to be on the hypotenuse. So this would have to be the 5 side. Well, so I'm going to notice that this is 10 times 5, and this is 10 times 4. So I guess the missing side must be 10 times 3. So x equals 30. Okay. And then one more here. We got 10, we got 24, and we got an x. So there's no 3, 4 going on here. 3, 4, 5, because it just doesn't look like it would work out here. But I would observe, basically, look at the two numbers you're given. Is there anything that both of them can be divided by? And in this case, they can both be divided by 2. This is 2 times 12. This is 2 times 5. And I'm going to observe, oh, 5 and 12, the other side was a 13. So this would be 2 times 13. So x equals 26. Okay. Again, if you don't notice this, you're fine. Just do Pythagorean theorem. Also, I want to point out something important here. This only works, as I said, this only works if the bigger number on the list is the hypotenuse. What if I gave you this triangle right here, where this is a 3 and this is a 5? Some people might look at that and say, oh, I guess the missing side's a 4. But notice that if you put a 4 here, the bigger side is not the hypotenuse, right? So that doesn't work. To solve this problem, you know what? If a Pythagorean theorem or a Pythagorean triple doesn't work, that's fine. You can do a Pythagorean theorem. 3 squared plus 5 squared equals x squared. That will always work. It's just if you notice this Pythagorean theorem, you can save this Pythagorean triple. You can save yourself some effort. Okay, the next thing we need to talk about here is a couple of special right triangles that are going to come up a lot. And so we want to make sure we understand them. Okay, so this is a good way to save time. Cool. Special right triangles. Okay, the first special right triangle we're going to look at comes from this square. Okay, so we're assuming this is a square. We're assuming that all of the sides are ones. The question that we want to ask is, what is the length of that diagonal? So I'm going to call that x. And to find that, we're going to look at this right triangle right here. And we're going to say that, oh, we can use Pythagorean Theorem, 1 squared, oops. Okay, so 1 squared plus 1 squared equals x squared. 1 plus 1 is 2, so 2 equals x squared, so x equals the square root of 2. So this missing side here is the square root of 2. Another question that we can ask, and then I'll get to the point here. Notice that when I draw that diagonal, it's bisecting each of those corners. It's cutting them in half, which means that this little angle right here is going to be 45 degrees. And in fact, the one on top will also be 45 degrees. Each of those is half of the corner of the square. Now, let me show you why that really matters. Let's now look at this triangle here. This right triangle, 2 of the corners are 45 and 45, and the other is 90. And notice that not only that, we also know all 3 sides of the triangle. The 2 legs are both 1s, and the hypotenuse is radical 2. By the way, notice, this is an isosceles right triangle. It's isosceles because both legs have a length of 1, and it's, of course, a right triangle. This is going to be our first special right triangle. In fact, we have a name for that. We're going to call that a 45-45-90 triangle. You could also, if you want to, you could call it an isosceles right triangle. Okay, because that is also a good name for it. So 45-45-90 triangle. The observation is, this is true for this triangle, sure. But if I were to multiply each of those sides by the same thing, I would also get a triangle that is 45-45-90. So each of those 3 sides, the 1, and the radical 2, I'm multiplying by some number that I'm just calling x. So this side would be 1 times x, 1 times x, and radical 2 times x. Every single 45-45-90 triangle has this form. So notice that if I knew the leg, I could find the hypotenuse by just multiplying by radical 2. That looks like x radical 2. Let's try that again. Here, times. Multiply by radical 2. If I know the leg, I can multiply by radical 2, and I will automatically know the hypotenuse. And if I want to go the other direction, well, then I'm just going to divide by radical 2. Okay? So this will help us, and we'll see an example in a couple minutes that demonstrates that. Let's get to first our other special right triangle. And we're going to assume that this is an equilateral triangle. I wasn't able to mark it very well, but we're assuming it's equilateral. So that's 2, the bottom is 2. And our question is, what is the height? So I want to observe that when I drop that height, this side ends up being half of the base, so that would only be 1. And so to find that missing height, I could do 1 squared plus x squared equals 2 squared. I'll subtract the 1 over, so x squared equals 3. So x equals square root of 3. Okay. So that missing side there is radical 3. The other thing I want to remind us is that when we saw the equilateral triangle earlier, we said that the corner here was 60 degrees. But that means when I drop the height, this little angle is going to be only 30 degrees. Again, because that 60 is being cut in half. This matters. This is useful because now let's focus on just that right triangle. And this is what we're going to call a 30-60-90 right triangle, or a 30-60-90 triangle. Again, it's not, this one happens to have sides of 1, 2, and radical 3, but multiply all 3 of those numbers by the same thing, and you would get another 30-60-90 triangle. So this is what our general 30, 60, 90 would look like, right? Multiply that 1 by x gives us x, multiply the 2 by x, and multiply by radical 3 by x. And once again, this shows us, hey, if we knew that this side was x, we could multiply it by 2, and that would give me this side. Or I could multiply by radical 3, and it would give me that side. And of course, division would take me the other direction. So dividing by 2 would take me that way, and dividing by radical 3 would take me that way. So we're going to play around with this in a second. Now, one feature of the 30, 60, 90 that I want to point out, please notice that x is across from the 30, and radical 3x is across from the 60. The smallest side, in this case, would be x, and that's always across from the smallest angle, which in this case is 30. All right, let's see how these can be useful. Okay, so let's find x and y. So for this problem, we were told that this angle is 60, and we have to be told that angle is 60. If that angle was blank, or if we didn't have if it was any other number, we could not use this method at all. These special triangles are just useful if we know that the angles are 30 or 60 or 45. If that's 60, then I know that this side's going to be this angle is going to be 30 degrees. And so now I'm going to be comparing this with my basic 30, 60, 90 triangle. Remember that in that triangle, the 1 was across from the 30, the 2 is across from the 90, and the radical 3 was across from the 60. So based on that picture, I'm noticing, oh, multiply by radical 3 gets me this way. So if I multiply this by radical 3, I'm going to get my x. X is equal to 8 times the square root of 3. So there's my x. And then I say, oh, if I want to go that way, oh, I'm multiplying by 2. Okay, well, then let's multiply this by 2. 8 times 2 gives me 16. So y is equal to 16. Okay. So comparing this with the basic 30, 60, 90 triangle is going to be helpful. And I want to emphasize, those of you who have taken geometry in the past, you might have seen this before. Regardless of if you've seen this before or not, this is really important. It's going to come up a lot. So it is definitely worth the time you put into understanding this. Let's try this problem. A house has a roof with a 45-degree pitch. If the house is 60 feet wide, find the lengths of the sides of the roof that form the attic round to the nearest foot. Okay, so because this is round to the nearest foot, that means that I'm going to use a calculator for this problem. That's great. It means I don't have to simplify any radicals. That's nice. This is a 45, 45, 90 triangle. We can see that in the picture. And so I'm going to compare this with the basic 45, 45, 90. Notice that I'm rotating it to look like the triangle that I'm given. And in this triangle, the two legs were both 1s. The hypotenuse was radical 2. So notice that to go from this leg to this side, we have to multiply by radical 2. But notice that for our problem, we want to go the other way. We want to go from the hypotenuse to the leg, which means this time I'm going to divide by radical 2. So I'm going to take that length that was given to me, that's 60. Oops. I'm going to take that 60, and I'm going to divide it by radical 2, and that's going to give me x. By going one way, we multiply by that factor. Going the other way, we divide. So at the bottom here, we went from the leg to the hypotenuse, multiplying by radical 2. In the picture, we go from hypotenuse to leg, so we have to divide by radical 2. Anyway, I'm going to use my calculator. I'm going to calculate 60 divided by the square root of 2, and I'm getting 42.4 feet. There we go. Okay, so that brings us to the end of section 1.1. Now we're going to move on to section 1.3, which deals with trigonometry. Okay, fine. This whole course deals with trigonometry, but specifically we're going to introduce trigonometry today. So first off, trigonometry is the study of the relationships between angles and sides of a triangle. And within a triangle, a comparison of the comparison of the lengths of two sides of a right triangle is called a trigonometric ratio, and the three primary ratios of trigonometry are sine, cosine, and tangent. I guess kind of one way to introduce that would be thinking about this for a second. Notice that in the triangle on the right side, if I were to do 2 divided by 1, I'm going to get a ratio of 2. If I did the same ratio on the left side, it would be 16 over 8. I'm still going to get an answer of 2. The observation is, no matter how big or small the triangle is, as long as those angles stay as a 30, 60, and 90, we always get the same ratio of 2 if those are the two sides that I pick. Trigonometry sort of formalizes that and says, okay, let's go beyond 30, 60, 90. Let's find a way of formalizing that for everything. So our three primary ratios in trigonometry are sine, cosine, and tangent. Now, to help us remember these different ratios, to remember what these ratios are, we have maybe a motto or a saying. The primary trig ratios can be found by remembering so, ka, toa. Now, I want you to repeat after me. Yes, I know you're watching a YouTube video. I don't care. Repeat after me. So, ka, toa. Now, you didn't do it. Now, I know you're sitting there, you're like, all right, I'm just going to wait him out. Repeat after me. So, ka, toa. And pronounce it that same way. Now, you have no idea what this stands for. That's what we're getting to now. So, ka, toa means that the sine of an angle, notice that the angle in the picture is labeled as theta. The sine of that angle, also please notice that we're abbreviating the word sine with the letters S-I-N. Okay, I'm still going to say sine. The sine of the angle is equal to opposite over hypotenuse. Now, first of all, we know without anything else, we already know that the hypotenuse is this side because it's across from the 90. The word opposite means across from. So when I want to pick the opposite side, I want the side that is across from the angle that we're talking about. If this says sine theta, we're talking about angle theta. The side that is opposite that would be this side right here. So that is my opposite side. Now, again, the side that we label as opposite depends on which angle the problem asks you about. In this case, the angle of theta is labeled there on the left, so the opposite means across from it. So sine is opposite over hypotenuse, SOH. Cosine, which we're going to abbreviate COS. Cosine of theta is equal to adjacent over hypotenuse. Now, adjacent means next to. So here's my theta. Adjacent means the side that is next to it. Well, it's not going to be this side because we already have a name for that one. That's hypotenuse. So adjacent means next to. Maybe instead of adjacent, maybe I want to say adjacent leg. Which leg is next to our angle? And that would be this one right here. So this side is the adjacent side. Again, adjacent means next to, but not hypotenuse. So cosine is adjacent over hypotenuse. Say CAH. And then finally, tangent of theta is equal to opposite over adjacent. So again, tangent we're abbreviating with TAN or TAN. Okay, these are the three basic trig functions: sine, cosine, tangent, and then SOHCAHTOA helps us to remember how to calculate each of these ratios. There are actually a total of 6 trig ratios. These are the first 3. The other 3 trig ratios are called cosecant, secant, and cotangent. And in fact, all 3 of these are based on the first 3. Cosecant, which I'm abbreviating CSC. Cosecant is 1 over sine. So cosecant of theta is 1 over the sine of theta. Secant, which I'm abbreviating SEC. Secant of theta is equal to 1 over the cosine of theta. And then cotangent, which I'm abbreviating COT, is 1 over the tangent of theta. Okay, so using this, let's find our 6 trig ratios for theta in this picture. So, in order to answer this question, first we actually need to know all 3 sides of the triangle. So let's try to figure out the third missing side of the triangle. Go ahead and do that on your own. Pause the video, and then we'll talk about what the correct answer is. Hopefully you noticed that, oh, look, there's a 3 and a 4, so I guess this missing side must be a 5. This is a 3, 4, 5 triangle. Again, you can use Pythagorean Theorem. There's nothing wrong with that. But notice you don't have to. Okay, so we're going to find, let's start with the sine of theta. Now, sine is, again, it's sine, here, right at the bottom. Sine is opposite over hypotenuse. So here's my theta this time. Again, opposite means across from. So the side that's across from that angle is at 4. So 4 goes on top. And in this triangle, hypotenuse is the 5. So in this problem, the sine of theta is 4 over 5. And right now, that's all you need to do. That's all we're doing here. Okay, we're going to do a whole lot more of that very quickly. But for right now, that's all you got to do. Okay, sine of theta is just this fraction. Next up, cosine theta. Again, we're going to focus on that theta that's given to us. So cosine, C-A-H. Cosine is adjacent over hypotenuse. Well, here's my angle. The adjacent side, the one that's next to it, is that 3. Remember, I'm not using the 5. 5 already has a name. It's called the hypotenuse. So the side that's next to this theta would be the 3. Over hypotenuse, in this picture, we already said the hypotenuse is 5. So the cosine of theta is 3 over 5. Tangent. So tan theta. Tangent is opposite over adjacent. Okay? Well, again, here's my theta. We already said the opposite side was 4. The adjacent side was 3. So there's those. And then for the other 3, cosecant theta, well, cosecant is 1 over sine. Guys, basically cosecant is the reciprocal of the sine fraction. So if sine was 4/5, cosecant theta is 5 over 4. Secant theta is the reciprocal of cosine. So if cosine is 3/5, secant is 5 over 3. And then cotangent is the reciprocal of tangent. So if tangent is 4 over 3, cotangent is 3 over 4. There we go. Okay. I'd like you guys to please try this problem for me. Find the 6 trig ratios. Go ahead and pause the video. And then resume it when you're ready to hear what the answer is. So the first thing I need to do is find the missing side. So I'm going to call it x. So we know x squared plus 7 squared equals radical 65 squared. So we get x squared plus 49 equals, remember the square root cancels with the squared, so this is just 65. If I subtract 49, we get x squared equals 16. So x equals 4. So I'll put a 4 here. Okay. So we're going to find sine theta. Well, let's start with sine theta. Okay. So sine theta, here's my theta. Here's the angle we're told to focus on. Sine of theta is opposite over hypotenuse. Okay, so the opposite side is 7. Hypotenuse is the square root of 65. Okay, before we go any further, I want to remind you that, as I said earlier, you need to simplify all radicals. So you may recall from previous classes, you can't leave a radical on the bottom of a fraction like that. You need to do what we call rationalizing the denominator. And to do that, we're going to multiply top and bottom by that radical we don't want to be there. So the top becomes 7 radical 65. On the bottom, radical 65 times radical 65 is just 65. So this would be my simplified answer for sine theta. Cosine theta is equal to adjacent over hypotenuse. Well, if this is my theta again, adjacent side would be the 4. Hypotenuse is still radical 65. Once again, I need to rationalize this. So multiply the top and the bottom by radical 65. Oops. So the top becomes 4 radical 65. The bottom becomes just 65. Okay. Tan theta is equal to opposite over adjacent. Well, for my theta, the opposite side we said was 7. The adjacent side was 4. So tan theta E is 7 over 4. All right, next up, cosecant theta. So again, cosecant is the reciprocal of sine. But, guys, use the original version of sine. Don't use the simplified version. And let me show you why. If we take the reciprocal of that original version, it's radical 65 over 7. You don't need to do anything. That is the simplified version already. Because when you do the reciprocal, there's no longer a problem in the denominator, so that's a good answer. Likewise, for the secant of theta, just take that original cosine fraction and flip it. We get radical 65 over 4. And then finally, cotangent of theta, we take the tangent fraction and flip it. We get 4 over 7. Okay. So for any right triangle, by the way, let me emphasize that. This is only in a right triangle. We're going to spend a long time on right triangles before we move to any other types when it comes to these trig ratios. So we could find all 6 of these trig ratios for that angle theta. All right, let's take a look at this problem. Now, I'm not asking for every single trig ratio for each of the angles. I just want these 6 ratios for these angles. So again, pause the video for a second. You try it. Try to find these 6 ratios for me. So let's do the left column first. The left column asks me to focus just on this angle alpha. Well, for this angle alpha, the opposite, again, opposite means across from is, so sine is opposite over hypotenuse. The opposite side is 12, and the hypotenuse for this problem is 13. Cool. Tangent is opposite over adjacent. So let's see here. So the opposite side would be 12. We already said that. The adjacent side would be 5. Okay, the next one here, secant. So before I do secant, let's start by doing cosine. Cosine alpha. Cosine is adjacent over hypotenuse. For this angle alpha here, the adjacent side is 5, and the hypotenuse is 13. So the cosine of alpha would be 5 over 13, which means that the secant would be the reciprocal, 13 over 5. Okay, so there's the alphas. Now notice for the next column, we're switching our focus now to the beta. So let's talk about the cosine of beta. Cosine is adjacent over hypotenuse. Well, for this beta, now the adjacent side is this 12. And the hypotenuse is 13, right? That doesn't change any. But again, notice, when we talk about opposite or adjacent, it all depends on which angle you're asked to focus on. Right? The opposite side for alpha was not the same as the opposite side for beta. Cotangent of beta, let me start by finding the tangent of beta. Tangent is opposite over adjacent. So for beta, the opposite side is 5. The adjacent is 12. Again, opposite means across from, adjacent means next to. So if tangent is 5 over 12, then cotangent is 12 over 5. And then before we do cosecant, let's do the sine of beta. The sine of beta, again, sine is opposite over hypotenuse. So for beta, opposite side is 5, hypotenuse is 13. So the sine is 5 over 13. So the cosecant is the reciprocal, 13 over 5. Okay, we're doing this problem for a reason. And we're observing that, oh, look, we got the same answer in a couple of different ways. Now, one observation that I want to point out is in this triangle, please notice that alpha plus beta is equal to 90. And the reason is, if all three corners have to add up to 180, but one of them is already 90, that means that there's only 90 degrees left for the other two. So these two angles, alpha and beta, are complements of each other. They're complementary. They add up to 90. And the observation we can make here is, this is called the cofunction theorem. The observation we can make here is, if alpha plus beta is equal to 90, then that means that the sine of alpha is equal to the cosine of beta. And maybe that's why it's called the cosine, because they have that relationship. The tangent of alpha is equal to the cotangent of beta. And the secant of alpha is equal to the cosecant of beta. So if you have two angles that are complementary, one of the trig ratios for one angle is equal to the co of the trig ratio of the other angle. I don't know if that made any sense, but whatever. And we can state that as an identity. We're going to have a lot of an identity. Let me start with this. An identity just means an equation that is always true. And we're going to have a lot of those throughout this course, a lot of them with regards to trig ratios. And so we're just starting off right here. Oh, the parentheses didn't come out. Let me draw those in there. So the sine of alpha is equal to the cosine of 90 minus alpha, right? If this, I'm sorry, I meant theta. If this is theta, 90 minus theta, wouldn't that just be the complement? Right? Because if they add up to 90, if we know one of them, we can subtract from 90 to find the other. So the sine of one angle is equal to the cosine of its complement, 90 minus theta. Anyway, these are definitely two things that you want to make sure that you're starting to commit to memory. You're definitely going to need to know a lot of trig identities, and this is just the start of that list. So one way that can help us is, let's say we want to find these. Now, I'm not actually asking you to evaluate these. I don't want a number. All I want to know is, what other trig ratio is this equal to? So, for example, the sine of 30 is equal to, well, the sine of 30 is equal to the cosine of the complement of 30. Right? So the complement would be 90 minus 30, which is 60. So the sine of 30 is equal to the cosine of 60. Now, I don't know what those two numbers are. We're actually going to get to that in the next lesson. But right now, all I know is, hey, these are equal to each other. Likewise, the cotangent of 57 is equal to, well, the co of that would be the tangent. And the angle that I'm looking for is going to be the complement of 57. 90 minus 57 is 33. So the cotangent of 57 is equal to the tangent of 33. And then finally, the secant of this angle is equal to the cosecant of its complement. Well, 83 subtracted from 90 is 7. So again, I don't know what all these values are, but I certainly know that they are equal to each other. Okay, let's take a look at one more example here. In the triangle, sine theta is equal to 5 over 13, and the perimeter is 60. We want to find the length of the hypotenuse. Cool. Now, the thing I want to point out is this. If we had, let's talk about a fraction here. If I had a fraction, I don't know, 15 over 25, I could reduce that to 3/5. And the reason that I can reduce it is because if I were to multiply top and bottom by the same thing, here it just happens to be 5. If I were to take the 3 on the top and the 5 on the bottom and multiply them by the same thing, I would get the bigger fraction, 15 over 25. Right? That ratio, that 3/5, is just the reduced version of that fraction. Likewise, this 5 over 13 is the reduced version. And here's how I know it's reduced. Just for a moment, let me write in here. Well, let's see. Sine is opposite over hypotenuse. So if this is my theta here, the opposite side would be 5, and the hypotenuse would be 13. Because, opposite over hypotenuse is 5 over 13. And by the way, just as long as we're thinking about it, we can also find the third side. Notice that these are part of a 5, 12, 13 triangle. That was one of our Pythagorean triples. So these two sides, if those are the two sides, this side will also be 12. Again, if you don't notice that, don't worry about it. Use Pythagorean Theorem. 5 squared plus x squared equals 13 squared. You'll get the same answer. But I want to point out these numbers are too small. Because if I add these together, I'm not going to get 60. They're too small. So what that tells me is this 5 over 13 isn't the numbers from the triangle. That's the reduced version of the fraction. The actual numbers of the triangle were 5 times something and 13 times something. And I don't know what that something is, but I know that multiplying top and bottom by the same thing will get the numbers big enough to be the actual sides of the triangle. So these two sides are actually 13 times x and 5 times x, and the missing side here will be 12 times x. So to figure out what x is, now we're going to use the fact that, the perimeter is 60. So if I add up all the sides, 5x plus 12x plus 13x, the answer is going to be 60. Add those together, I get 30x equals 60. So x equals 20. Nope, x equals 2. What have we got in there? Okay, so x equals 2. Cool. We're not done though, but that definitely helps us. So basically I should have just doubled the numbers of the fraction that was given to me to get the actual side lengths of the triangle. The last question here is we need to find the length of the hypotenuse. Notice that the hypotenuse is that 13x. So now that we know that x is 2, hypotenuse is equal to 26. Okay, that concludes our first lesson.